All right, everyone. Welcome to lecture 17 for the semester. So we're starting to wrap up our discussion of partial derivatives, and then we'll move on to the multivariable analog of integration next. But before we leave derivatives behind, one of the main uses of derivatives of any sort is to find the maxima and minima of functions. And this is definitely something that we managed to do in Calculus 1 here. Before we get going, though, I just want to remind everyone that at least for this class, there's nothing tomorrow for the recharge day. So there's no discussion section or anything like that. Just wanted to remind you guys about that. Anyways, let's continue here. So let's remember back in Calc 1. So we use derivatives to find out the maxima and minima of functions. And where did those happen? They happened at critical points where our derivative was either 0 or occasionally it was at a place where our derivative didn't exist. Like, for example, you could have a minimum value where we have a cusp and our derivative won't exist there. It's easy to forget about this case, but it does show up sometimes. Those are the places where maxima and minima can occur. So we had two main results about this. If f has a local max or min at a point, and if f prime of c exists, meaning it's not this, well, then by process of elimination, f prime of c needs to equal 0. So most of the time when we want to find our maxima and minima, we just set the derivative equal 0 and see what happens. And spoiler alert, we're essentially going to do the same thing today. The second derivative test can help label whether we have a local max or local min. So this is good at finding where they may be. This one is good at telling what they are. So if we have some kind of critical point, if we have f prime of c being 0, and f double prime of c is positive, then do you guys remember what the conclusion is? Then c is a local, which one was it? The minimum, that's right. Yes, remember f double prime of c being greater than 0 means you're concave up. So you're looking like this, you're opening upwards, you look like a smiley face. So we're going to be a local min there. And on the other hand, if we have this being negative and we're a frowny face, we're concave down, then C is a local max. But remember that this is not always conclusive. When was this not going to be conclusive? And when we have to do something else? There's one case not covered between these two. That's right. So if f double prime of c is 0, then we need to do something else. It doesn't mean that the answer doesn't exist. It just means that the second derivative test can't tell us what's going on. All right. So that was for finding local mins and maxes. So that would help you find the largest or smallest point in a certain region. So for example, if we have a function like this, this would be considered a local maximum. But these things don't tell you anything about the possible absolute maxes, which would be over here. So this is for finding local mins and maxes. If you want to find absolute or global maxes and mins of a continuous function, they can occur either at the critical points that we talked about earlier, or they could appear at the endpoints or the boundaries of our graph. So all the possible candidates for absolute maxes and mins in this graph, for example, would be right here. Right here, we have a derivative of 0. Here we have another derivative of 0. Here it looks like a cusp, so the derivative is undefined there. Another derivative being 0. We have one here, and then we have one there. So what we do is we take all of the critical points and we compare them, and we see which one gives the highest function value, which one gives the lowest function value. So if we do so, this would be the absolute max, and this would be the absolute min. And as you can see from this example, sometimes it happens at an endpoint, and sometimes it happens at a critical point. We can't really be sure until we plug all of them in, because the situation changes every single time. All right. So now that's a little Calc 1 review. That's what we've already done. Now, I want you guys to keep this in mind when we talk about multivariable functions, because it's going to be almost exactly the same thing. It's going to be the same types of ideas for this. So a function f of x, y, so now we have two variables, has a local maximum value at AB if f of AB is greater than or equal to f of xy for any x and y near AB. And it has to be in the domain as well. All right, so that's what a local maximum is. It's bigger than any point in the immediate vicinity. So the 3D example would be kind of like a bulge. Like if we have a little bit of a bulge, the top of the bulge would be a local maximum. But who knows what happens outside of that hill? And then in the same way, a local minimum value is going to be less than or equal to everything in the immediate vicinity. All right, now how do we find these local extrema? Well, I've already spoiled this from earlier. Well, we're going to find the critical points. And the critical points are where we have both of our partial derivatives equaling 0, or one or the other does not exist. So it's almost exactly the same definition that we had in Calc 1. Another way of imagining this is saying that the gradient is the 0 vector. So if your gradient is the 0 vector, then you're going to have a critical point at wherever that happens. So that's another way of thinking about this. All right, well, let's give it a shot here. Let's practice doing this. Let me organize my papers just a second. Okay. Find all the critical points for this function. All right, well, the critical points have to do with our partial derivatives, so let's find those. So let's see, what's my x derivative going to be here? It's going to be 4x cubed minus 4x, and then all of this will go to 0. Okay, let's take a look at the y derivative. These will all go to 0. This will be 2y, and then this will be just -4, and then that's it. All right, now we need both of these to be 0 at the same time. Right here. So that gives us two equations here. So the first equation, or actually I'm going to look at the second equation because that one's easier. I'm going to procrastinate. We have 2y equals 4, meaning that at whatever point we have that's going to be a critical point, the y value has to be 2 there. So we know that. Now let's take a look at what we have here. We have 4x cubed is equal to 4x. Well, with that, we can simply divide by the 4s, and we get that x cubed equals x right here. All right, now there are 3 different x values that satisfy this equation. What are they? -1, 0, and 1, absolutely. So these are our possible x values for the point. Now what we do is we take all of the possible x values and combine them with all of the different possible y values, because as long as one of each of these is satisfied, then both of these will be 0. And that's the main point, is getting both of these to be 0. So that means that our critical points will end up being -1, 2, 0, 2, and 1, 2. All right. So then one thing to watch out for is we need to check also where this may be undefined, but this is a bunch of power functions, so that's not going to be undefined anymore. So we're good to go here. These are our 3 critical points. Okay. All right, now here is the higher dimensional version of Fermat's theorem. So if f of x has a local max or min value, and they both exist, meaning you don't have any DNE situations, then the derivatives must be 0 where you have a local max. And this was what I was kind of talking about earlier. So imagine that we're at the top of a hill right here. And then we take a look up here. Here's the local maximum. It happens when both our x and y derivatives are 0. Now, another way of saying that, it's equivalent to the tangent plane being flat or perfectly horizontal. And why is that? Well, here's the equation of the tangent plane, right? It's z minus f of AB is fx times x minus a plus fy times y minus a. But then what are these two guys going to equal here? This is going to end up equaling 0. So this entire psi will be 0 because these will be zeros. And then we can just move this over here. So we end up with z being some constant value, which we could just call c. So this means that our tangent plane is going to be entirely flat right here. When would our tangent plane be entirely vertical? It'd be vertical if we were missing the z component, so we can have any z value that we want. That would be an occasion when our tangent plane would be vertical. But that would violate this condition up here, so we're not going to think about that for the time being. All right. Now, let's say we've identified a critical point, right? Does f have a local maximum or minimum there? Or rather, does it have to have a max or a min right there? What's the difference between a tangent plane and a flat tangent plane? I mean, a flat tangent plane is just flat. Like it's just a specific plane in a particular direction. Like if you could just draw the plane like this, it's totally flat. All right. I guess maybe you're confused by the fact that all planes are kind of flat in a certain sense. I mean horizontal. I mean horizontal. So it's going to have the equation z equals something. I guess that's what I mean by that. Yeah, you could say it's parallel to the xy plane if you want. There we go. Hopefully that's enough to describe what I was talking about here. Okay, now here's the question again. So if we have a critical point, does f have to have a local max or min at a, b? Well, let's find out. So here we have another function. Let's look at partial f partial x. That's going to be easy. It's negative 2x. Then we have partial f partial y right here. That's going to be 2y. Now remember, for these, we want the critical points to be, we want both of our partial derivatives to be 0. But then that immediately tells us what x and y have to be. We end up seeing that the point 0, 0 is going to be our critical point right here. All right, now this is everyone's favorite Pringle graph right here, or the hyperbolic paraboloid. 0, 0 is right here, and you can see kind of just barely at this moment, it's going to be flat. But is it going to be a local max? Well, not really, because we can go up the sides either way and get a bigger point. Is it going to be a local min? Well, that's also not true, because we can go down the side of the saddle this way, like this. So it turns out that this is not a max or a min. So it doesn't have to be, just because you're a critical point doesn't mean you have to be your max min, just like in Calc 1. Yeah.
Like the 3D analog for.
Yeah, that's right. Yeah. So someone asked, is this the 3D analog of inflection point? Yeah, essentially, yeah. That's what you're saying is true. All right. All right. Now, what is the name of this point? This is going to have the name saddle point, because near any one of these points where we have them not being a max or min, it's going to look like this, because it's going to go up in one direction and then it's going to go down in a different direction. So it's not going to be a max or min. So it's going to look kind of like this once you get close. Like it might be a little bit more smushed out or steeper. It may bend one way more than another, but it's going to essentially look like this right here. All right. So let's see here. Now we've identified a bunch of critical points, but how do we identify whether they are maxes or mins? Because sometimes they really are maxes or mins, and we want to know which ones are maxes and which ones are mins. All right, so how do we do that? Well, here comes our version of the second derivative test right here. So this is for functions of two variables. Now, most of the time when I talk about something in this class, it generalizes immediately. to functions of like 3 or more variables. This is one of the things that doesn't. So there is going to be something like this for functions of more than 2 variables, but it's not going to be this simple of a test. So this only exclusively works for 2 variables. But yeah, unlike most of the stuff which you could just immediately keep adding variables, keep doing it. In this case, you can't. All right, so let's say we could take all of the second partial derivatives that we want. So remember, there are 3 varieties of these. There's fxx, where we take the x derivative twice. There's fyy, where we do the y derivative twice. And then there's fxy, or fyx, if you like, where we take one of each. And remember, since these are all continuous, since we have this keyword right here, fxy will equal fyx right here. So what is this saying? So let's say we have all these second derivatives and they exist, and we're at a point where the derivative is 0. Then we compute this special number d, which is called the discriminant, which is the product of what are called the pure partials, fxx times fyy minus the mixed partials. Technically, this would be fxy times fyx, but those are equal. So we could just imagine it as this squared right here, pure. Okay, so what is the result of this? You know, with the second derivative test in Calc 1, we had like a nice, easy way of doing it. If it was positive, it's a min. If it's negative, it's a max. Here's a little bit trickier. If we have the discriminant being positive and our second derivative is negative, then we have a local max. So it's almost like getting into this mode right here enables us to use our old-fashioned verb form of the second derivative test, because we see a second derivative being negative and we get a max. And in the same way, if d is still positive, both of these are positive, but your second derivative is also positive, then you're going to get a local min. All right, now what happens if d is negative right here? Then f is going to have a saddle point at that point. So it's going to go up in some direction and then down in a different direction here. And then finally, if d is equal to 0, just like how the old version of the second derivative test was inconclusive, this one will be as well. So this is going to be our new version of the second derivative test right here. Typo should say single point. Oh, what is fxx? Oh, it's this where you take 2 x derivatives. That's what this is talking about here. All right. If d is equal to 0, all right, yeah. So someone asked, why? What if d is equal to 0? Do we just panic? Are we done for? Well, in that case, you may want to find a picture of what's going on and then take a look at it there, or use other properties of the functions to determine whether it's a max or min or maybe a saddle. All right. Why does 2x derivatives determine it though? And why not y? You can use y if you want. So you could replace these with y and it would still work. It's just, I don't know, you just pick one of them and see if it's going to be positive or negative. So it's either pure partial, that's right. All right, let's go ahead and do this. So find and class, well, let me keep this up so we can refer to it. What is d a measure of? I don't think I can really talk about that now because you guys haven't had linear algebra. Technically, d is a determinant of something called the Hessian matrix. But other than that, I can't really go too much into detail why this specifically works. All right, find and classify all critical points here. All right, well, first of all, we need to know where the critical points are. So that's where our first partial derivatives come in. Let's see, what's the x derivative here? If we take the x derivative, we have y squared minus 12x, and then that'll be 0. All right, fy will be 2xy. This will be 0, and then we have minus 6y. All right, so let's see here. What I'm going to do first is I'm going to look at this equation. So if I move the 6y over, I have 2xy is 6y. Well, there's one obvious way that this equation can work here. What's one way that this equation can be satisfied? Y equals 0, that's right. Okay, so y equals 0 will work for this. And then what you could do is you could take that and put it into here. So if y is equal to 0 and we use that information, then we put y is 0 here, and we have negative 12x is 0, meaning that x is 0. So if we're using the way of doing this where y is 0, then x is forced to be 0 as well. So 0, 0 is going to be a critical point here. Okay, now let's say we didn't do that. Let's see if there's another way we can solve this. So I'm going to divide out the y here, and I have 2x is 6, or x is 3. So now I'm going to use the x equals 3 way of doing this. I'm going to take it and put it into this equation. And I have y squared minus 36 is 0. So in the situation where x is equal to 3, y can be plus or minus 6. So this actually gives us 2 more critical points. We also get 3, 6, and 3, negative 6 as well. Now you might be wondering, okay, why can't we do something like 3, 0? Why can't we do that then? Because if we use the way of doing this where we have 3 right here, then we can't just use y as 0, because then we would have negative 36 is equal to 0. So if we solve an equation one way, we need to be consistent with how we substitute it in the other. So we basically solve like a system of equations. Yes, that's exactly what we're doing right here. All right, so these are all of our critical points right here. So let's classify each of them, meaning let's compute D for each of them. Now, in order to compute D, we need to know what all of the second partials are. All right, so let's figure that out. What's the second x derivative? Well, I do an x derivative of the x derivative. I got negative 12. What's the pure partial for y? Let's see, I get 2x minus 6 for that. And then hybrid, the mixed partial here, what's that going to be? I do the y derivative of this or the x derivative, either way is fine. And I get 2y. Okay, so it looks like D, which is fxx fyy minus fxy squared, is going to be negative 24x plus 72 minus 4y squared. Because I'm doing these multiplied together, and then I subtract this squared right here. How did I get x equals 3? I divided both sides by y, and I had 2x equals 6, and then I got x equals 3. All right, so now we just need to test D for each of these values here. So D of 0, 0. Well, let's see. So I plug 0 in for these, so I just have positive 72. All right, and we see that we get a positive number. Now let's remind ourselves what the test was again. So let's see, so we have a positive value here, then let's check fxx. So fxx is less than 0, because it's going to be negative 12 no matter what value you plug it in. So then we have that being less than 0, meaning that we are going to be a local maximum. All right, let's try 3, 6 now. So let's see here. We're going to have negative 72 plus 72, and then minus 4 times y to the 6th. So that'll be minus, let's see, 36 times 4 will be 144. So we have negative 144 for this, and we actually don't need to do anything else. Since this is less than 0 and our D value is less than 0 right here, what's going to happen? We're going to have a saddle point. Okay. All right, and then the final one, let's see, I plug 3 into here again. Still have that constant 72. And then since this is squared, it's still going to be the same thing. So we have that being less than 0, and this will also be a saddle point. So there we go. So we were able to classify this into all three of these right here. All right. The first one should be greater. I'm not sure what your, yeah, fxx is negative 12. So I'm pretty sure this one is going to be negative here. All right. Anyways, let's go ahead and continue here. Let's try another one. Let's find and classify all the critical points for this guy. All right, well, let's see. We need to know fx and fy. The x derivative will be 8x cubed. And then the y derivative will be 4y cubed. Now, we want both of these to be 0 at the same time. So what point is going to satisfy both of those right here? It's just going to be 0, 0. That's the only way we can have these equations work. All right, 0, 0 is our critical point, so let's classify it. In order to do that, we need the second partials. fxx is going to be 24x squared. fyy is going to be 12y squared. fxy, well, if I do the y derivative of this or the x derivative of this, I get 0. Meaning that my d will be 288 x squared y squared. All right. So we get that. All right, now let's go ahead and plug in the point. So d of 0, 0. Well, uh-oh. All right, so I have 0 times 288. That's 0. So it seems like we're going to get inconclusive for this one. So the second derivative test can't tell us whether this point is a local min or a local max. Now, what's really the answer? Is this going to be a local min or a local max? What do you guys think? And as a hint, take a look at the original equation here. Think about the properties. A lot of people are saying min. Can anyone explain why it might be a minimum? That's right, because x to the fourth and y to the fourth, those are both greater than or equal to 0, right? So that means that this whole thing is greater than or equal to 0. So if we plug in the critical point 0, 0, we get actually 0 for this. So that means that every other point in the vicinity and actually everywhere will be greater than or equal to the value that we put in for 0, 0. So this is really a local min, but not from the second derivative test. All right, so that's our conclusion for this right here. All right, so that's enough about finding a local extrema. You find the critical points by setting the derivative equal to 0, and then you use the second derivative test, or you use properties of the function in case this doesn't work. All right, I'll explain one more time. Well, so at our critical point, if we plug that in, we have 0, right? But since these are x to the fourth, both of these are greater than or equal to 0, meaning the sum of them will also be greater than or equal to 0. So this means that this function is going to be greater than or equal to the value at our point everywhere. Okay, so let's talk about absolute maxes and mins. So f has an absolute maximum at AB if f of AB is greater than or equal to f of xy for any point xy in the domain of f. So we're not just considering a nearby area here, we're looking all over the domain of f. And no matter how hard we look, we can't find any point that's going to be less than, greater than the value of this. And absolute minimum is defined in pretty much exactly the same way. It's that every point will be greater than or equal to this. Okay, now let's take a look at the extreme value theorem, which is essentially going to be the same thing that it was for Calc 1, only stepped up a dimension. So let's suppose that f of xy is a continuous function on a closed bounded set D. So that means that our domain can't go off forever. It has to be limited in some way. then f has both an I guess we should say absolute max and absolute minimum value on the domain. And here's the important part. This is going to help us actually solve the problem here. The extreme values occur either at the critical points or in the interior. Or sorry, they're going to be at the critical points in the interior or on the boundary. So if we go back to the picture that we had in the very beginning of class here, remember when we had our extreme value theorem here, the absolute could happen at one of the endpoints or it could happen somewhere in the middle. That's what this is saying here. It could happen on the boundary, which is now more than just a point, or it could happen somewhere in the middle at a critical point. All right, so let's take a look at this. Let's see how this is done. Find the absolute extrema of f of xy is x squared minus y squared minus 1. On the disk, x squared plus y squared is less than or equal to 1. So if we were to draw a picture of the domain here, x squared plus y squared equals 1 is the unit circle. So then x squared plus y squared less than or equal to 1 would be everything in here. So this is the domain. These are the points that we're allowed to put into our function, including ones on the edge of the circle here. And we're trying to find out which one of these points gives the largest output and which one gives the lowest output. All right, so let's go ahead and get started. So remember, they can happen at the critical points of the interior. So we first need to find the critical points. So that means we need to find fx and fy. All right, let's see, fx, that's not gonna be too hard, it's 2x. Fy, also not too bad, it's negative 2y. And as before, the only way to solve both of these simultaneously is going to be at 0, 0. So just like in Calc 1, remember, you may remember that we drew a chart. We have all of our points, and then we see what function value we have. So the first point we're going to put on this list is 0, 0. Now, what we're going to do is we're going to put a few other points on there, but those points can only come from the boundary. Now, what's the boundary of this region? The boundary of this region is the unit circle. So this was the interior part. This was in the middle right here. And then now we're going to have the boundary. Oh, what exactly defines extrema in 3D? Furthest from the origin, not furthest from the origin, highest or lowest z value. So remember, this is technically z equals f of x, y. So it's just the highest and lowest z value. All right, now we're going to look on the boundary here. And like I just said, the boundary or the edge of this is the unit circle. So you have x squared plus y squared equals 1. And a lot of times when you're given an inequality that defines the domain, usually just replace the inequality with an equal sign, and that should give you your boundary. Now, what we're going to do is we're going to substitute this in to x squared minus y squared minus 1. So let's see here. I'm going to solve this for y squared. Y squared is 1 minus x squared, right? So that means that I can replace this y squared with that. So I have x squared minus 1 minus x squared minus 1. And then what is this going to simplify to? Well, I have x squared minus negative x squared will be 2x squared. And then I have minus 1 and then minus 1. All right. So on the boundary, my function is going to be 2x squared minus 2. We can simplify it to that. Now, we don't want to just put any point that satisfies this on here. That'd be way too many points. We want to just pick the largest and smallest points that we can find on here. So how do we find the largest and smallest points of a one variable function? Well, we go back to Calc 1. So what we could do is we look at the derivative of this, and we have 4x, and we want to set that equal to 0 right here. We could do the same thing when solving for x, right? Yeah, so we could have also done x squared is 1 minus y squared, and we could have done a similar calculation. That's right. Okay, so x equals 0 is a crit point for this sub-problem. And then we take the two endpoints. Now let's see here. What are the endpoints of this? We can't just take any value on here. Well, what's the lowest x value we can have? The lowest x value we can have on our boundary is -1. And then what's the highest x value that we can have? Well, it's 1. So I'm sort of doing like a little mini version of this problem right here, where I take the critical point from this, and then I also take the boundary points here. And I'm going to see which one of these gives the highest and lowest x values here. All right, so if x is 0, or actually, sorry, I don't want to do this. I want to see, yeah, I guess that's the same thing. I want to see what my y values are here. So if I have x is 0 right here, I have 0 squared plus y squared is 1, because remember, we're on the boundary of this, right? So what can my y be in that case? So it could be 1. Yeah, it could also be -1 as well. What is the boundary? It's the unit circle. It's the edge of the x and y values I could plug into my function. All right, so I could have the point 0, 1 or 0, -1. Those could be my extreme values, which I'm going to test up here. All right, and then if I plug in x is -1 into here, I have 1 squared plus y squared is 0. Well, that means, or sorry, not 0, 1. That means that y is supposed to be 0 right here. So I plugged in the original y not f of x. I kind of made a mistake in describing this. I want to find all of the critical and boundary points for this, and then I want to substitute them into here so I can see what the matching y value is going to be. Because remember, my whole goal is to test points that are on this boundary, so I need to take these x values and put it into the boundary equation to get y. How do we get 1 and -1? Y squared equals 1 right here. And then I take 1 and put it into here, but then that will be 1 squared again, so we get 0. So this gives me 2 more points. It's -1, 0, and 1, 0, which I'll also put up here. All right. Can we plug it into the y squared equation too? Yeah, that's fine. However you want to use this, the boundary equation, you can plug it into there in any way you want. How do we get the boundary of the f of x equation? The lowest x value we have on our boundary is -1, and the highest x value we have on our boundary is 1. That's where that came from. Why do we have to sub the boundary into f of x, y? Because we want to get the highest and lowest x values there. So what's on the boundary mean? We're plugging in a point that's on the unit circle. So remember, this is the domain of the function. I'm not graphing the function here. This is not the graph of this in any way. This is the domain of this. These are all the acceptable x and y values that we can plug into here. So these are all the acceptable x and y values we can plug into here. And the extreme, the biggest output and the smallest output can happen either at a critical point here or somewhere on the boundary. And the candidates for which boundary points will work will just be finding the critical and boundary points in Calc 1 style back here. All right, well, now we actually have all of our points here. So now we're ready to just compare all of the sizes. So I'm going to plug 0, 0 into here, and I get -1. I'm going to plug 0, 1 into here, and I have 0 minus 1 minus 1, giving me -2. All right, looks like if I plug 0, -1 in here, I get the same thing. 0 minus -1 squared minus 1 is -2. All right, and then finally I have 1 and 0. So x is 1 minus y squared, which is 0, then -1 will be 0. And then the same thing happens because I square away this negative. So I have -1 squared minus 0 squared minus 1 will be 0. All right, so our final conclusion for this is that we have a tie for the absolute min. The absolute min is going to happen at 0, 1, and 0, -1. So it's going to happen here and here. And then we also have a tie for the absolute max. The absolute maximum value of this function comes from when we plug in either this point or this point. And it kind of makes sense if you think about it, right? Because you're subtracting y squared. So the more y you have, the lower value this function is going to be. So our lowest values will be when we're subtracting the most y squared. And our highest values come from when we have a big value for x squared. So that means that we look at the most x we can possibly be to get our biggest value. So intuitively, these answers kind of make sense. All right, I had a request to summarize this one more time. Oh, this graph is a Pringle? Yeah, this graph would look like a Pringle, exactly. And you can even test to see what type of critical point this is, and I guarantee you it's going to be a saddle point right there. So that's right, this graph's going to look like a Pringle. But anyways, let me summarize the process. We first find points in the interior that are critical points, and we do that the same way we did for local mins and maximums. And then what we do after that is we take our boundary equation, which is usually just replacing this with an equals, and we put it into the function. This should give us a one variable function, and then we find the critical points of this and the endpoints by looking at our domain. And we use those to get the other variables coordinate for that. So for example, we got 0, -1, and 1 here for x. So that means that the y value had to be one of these for the matching x values. And then finally, once we get all of these points, we also put them in the same chart as our earlier critical point. And then we just compare and see which one's biggest and see which one's smallest. So this, all of this stuff is the Calc 3 version of endpoints. Unfortunately, testing the endpoints got a whole heck of a lot more complicated in Calc 3. And these are just the normal critical points. So that's how you should kind of think of this. This is our new, unfortunately complicated way of testing the endpoints for our function. Because now our endpoint is an entire curve. It's the unit circle in this problem. All right. So, all right, so let's try this again, only with something a little bit different. Find the absolute extrema of f of xy is x plus y minus xy in this triangular region. All right, so let's draw this picture. Let's see, this triangular region has the point 0, 0, 0, 2, and then 4, 0, which is all the way out here. So the region that we're going, this is our domain, by the way. Every picture I'm drawing, this is the domain of f. All of the combinations of x and y values inside this triangle are okay to plug into this function. If I take, say, the point like 4, 4, which would be out here, that's not an acceptable point to put into my function here. This is just the domain of f. This isn't in any way a graph of this. That would need to be 3D. All right, so we're going to do the same thing that we did previously. We're going to find the critical points on the interior by looking at the partial derivatives. So let's see here. I'm going to do my x derivative, which is 1, 0, and then the x derivative of this will be -y. For fy, we have 0 here. The derivative of this will be 1, and then the y derivative of this will be -x. Okay, so we want both of these to equal 0 here. What does that mean our critical point is going to be right here? 1, 1, that's right. So when we assemble our little table of points to put, we know that 1, 1's got to be a member of that list. So 1, 1 would be somewhere like right here, probably. Now, if you get something that's obviously not in your domain, like let's say I solved these equations and got like 4, 7, which is definitely, it's going to be like way up here. It's not going to be in the domain at all. Then you could just omit it from the list. We only count things that are in the domain for this. All right, so now let's go ahead and find what the boundary points are. Now, unfortunately, for this problem, the boundary has to be split into 3 different categories because we have this side right here, we have this side right here, and then we have the hypotenuse right here. And all 3 of these have different equations. So this is going to unfortunately be a 3-step process now because we have to test all of the different edges of this triangle. All right, so let's test 1 first. What's an equation for this line right here? It's going to be x equals 0. Yeah, Michael has the right idea. X equals 0, y equals 0, and something we haven't computed yet. That's right. All right, so this one will be x equals 0. All right, what do we do with that? Well, we plug it into our functions. We have f of 0, y will be 0 plus y minus 0 times y, which will just be y right here. All right, so y is our simplified 1 variable function. And let's see, what's the restriction on y? Well, y has to be in between 0 to 2 right here, because our lowest y value here is 0, and our highest y value here is 2. Now, if we look at f prime of y, we end up getting 1, and 1 is not equal to 0, so there aren't any critical points for this, but we still could use the boundary points. So we're going to do 0 and 2 for that. And what are the matching x points here? Well, in this entire context, x is 0. So we're going to have those. So these are going to be our point. Well, actually, they're written backwards because we have yx. So we're going to get 0, 0, and 0, 2 as new points to test right here. All right, so we'll put them up here on our chart and come back to them later. All right, let's test the second edge now. Okay, so the equation of the second edge, it's a perfectly flat line along the x-axis. That's y equals 0. And f of x 0 will just be x in the same way that this just ended up being y. Okay, now what's the restriction on the domain for x here? What's the lowest and highest x values that we can have on this part of the boundary? 0 to 4, that's right. So we can go all the way to origin, and then we can go all the way out to the lower right edge, or the corner of that triangle. And just like before, if I were to do the derivative of this, I would just get 1. So there's no critical points I can get that way, but I can at least put the boundary points on here. And just as the same way we had last time, y needs to be 0 for all of this to even work. So these are going to be my y values. So I get the point 0, 0, which I actually already had from earlier, and I get 4, 0, which is new. All right, now the third one is going to be probably the trickiest one. So we first of all need to come up with an equation for this line. So let's see. So it goes down 4, it goes down 2 over a length of 4, meaning its slope is negative 1/2, and then it has a y-intercept of 2. So y is going to equal negative x 1 times 1/2 plus 2, or 2 minus x over 2. Now, just like before, I'm going to plug this into my equation. So f of x and then 2 minus x over 2 will be x plus 2 minus x over 2, because this used to be a y right here. And then we have minus x, and then y again is this right here. All right, so now we're going to combine all of this. Let's see, so I have negative 2x, negative x over 2, and positive x. All of that combined will be negative 3/2 x. All right, the only constant I have is a 2, and then I have plus x squared over 2 right here. All right, so now so this one we can find the derivative of, and it probably will be 0 somewhere. So f prime of all of this will be negative 3/2 plus x. So that means that we want x to be 3 halves right here. How did I get negative 3 halves right here? Well, I have x minus x over 2 and then minus 2x. All right, so x is going to be 3 halves for this one. But then remember, we also have the boundary points. But we actually already have both of the boundary points already on this list. We have 0, 2 here, and we have 4, 0 here. So it's no use writing them again because we already have them on the list. So let's just see what the matching y value for this is. So y is negative 1/2 times 3 halves plus 2. So we have negative 3/4 plus 2, which is 5/4. So that means that we have the point 3 halves, 5/4, which will be somewhere in the middle of this line. So it'll be kind of somewhere right there. Where did I plug that in? I plugged that into y. You always use whatever context you're in. So if x is 3 halves, I'm using this x and y equation right here to get y. All right, now that we've looked at all of the boundaries, we're good with the boundary, we're good with the interior. Now we're ready to just simply compare which one's the biggest, which one's the smallest. So if I plug 1, 1 into here, I have 1 plus 1 minus 1 is 1. So lots of ones. If I plug all zeros into here, I'm going to get 0. If I plug in x is 0 and y is 2, I get 2. If I plug x is 4 and y is 0 into here, I'm going to get 4. And then this last bit's going to be a little bit strange. So if I plug 3 halves, 5/4 into here, then I'm going to have, let's see, 3 halves plus 5/4 minus 15 over 8. Oh boy, so we have 12/8 plus 10/8 minus 15/8 will give us 7/8. All that work, and that didn't even end up being one of the extreme points right here. All right, so we see that this point is going to be our absolute max. We have absolute max here at 4, 0, and we have our absolute min here at the point 0, 0. All right, that one was a doozy, and doing things with boundaries tends to be pretty difficult. So next time we're going to learn a special way of doing optimization problems with boundaries. So we'll get to that next time.